Okay, in this lecture, we are going to learn about attention mechanism. Attention method is quite important uh, technique in deep learning. It was introduced first in 2004 and has a great impact in the area of natural language processing and computer vision. There's a relatively new uh, you know, a relatively new architecture in deep learning called transformer. And transformer was introduced in 2017 in a paper called Attention is All You Need. And transformer somehow replace all uh, usage of RNN and LSTM in many applications. So it's quite important, and transformer was a breakthrough, so we have to learn about transformer in details in this course. And it's based on attention, so attention by itself, even without transformer, has a great impact. So in this lecture, I'm going to go through attention in details and the history of attention and details of each major contribution. But before we talk about attention, let's talk about a more general concept, common representation. In many cases, you want to translate or transfer, a concept from one domain to another domain. So, for example, you have, a word or you have a sentence in one language, and you want to translate it in a different language. Or imagine that you have an abstraction, a concept in your mind. Forget about neural network. You have an abstraction in your mind, and there are many different ways to represent the abstraction that you have in mind. You have the concept of elephant, not the word of elephant, in your mind. And you can represent this concept as word elephant in English. So basically, you can represent it as word elephant in English. You can represent it as word feel in Persian, or you can represent it as, say, sorry, I'm not a good, you know, you can, represent it as like a cartoon of elephant. Uh, but all of them, all of these different representation comes from a common concept in your mind. Okay, think of this vector as this common vector in your brain, in your mind, and think of this as a decoder, which take this concept from this abstraction and represent it in different ways. It can represent it as elephant. I can have another decoder which represented as feel, and I can have another decoder which represented an image, right? So this is my target domain. Okay, and I have a source domain. So if I have a mechanism to take my my source domain and translate it to this common vector, such that this common vector can be passed to another function, which is my decoder, and then this decoder translated to basically the concept in different languages or images or whatever. I can go from one domain to another domain. And this is basically the concept of encoder decoder. So we have encoder, which is usually a neural network, and we have a decoder, which is usually another neural network. And the idea is that the encoder translate, a concept from one domain to a vector, which can be decoded to different concepts. Okay, so it's quite useful concept to have in mind, and in a sense, the whole deep learning is about representing your knowledge. This is how I represented my domain knowledge, my source knowledge. So the whole deep network is about uh, learning features, or basically representing your knowledge. Is about knowledge representation. Is about representational learning, say. Okay, so uh, have this concept in mind. Now let's look at RNN, that you already know about RNN. RNN can take care of sequential data, and it takes two inputs and two outputs, and these are the two inputs. A hidden space and the observation, and it combines the hidden space and observation and makes a new hidden space, right? And an output. So we have the concept of Markov chain here, and each step, I assume that the whole knowledge of the past has been distilled to the current state, to the previous state. Sorry, at the current state, I assume that the whole knowledge of the past has been represented here, right? And then I combine this with my current observation, and then I produce a new hidden space, which is distillation of everything so far. Okay, you're familiar with RNN. And suppose that you have two RNNs, then one of them is going to be your encoder, and the other one is going to be your decoder. Okay? So now suppose that you want to do a task like translation. In the source language, you have a sentence, say, student, right? Okay, you pass I to your unit of RNN, and given your observation I and given the previous state, you produce a new state, which is a representation of this word, and then you pass a new word, and then your state here is going to be basically a vector which represents both I and am, and then you pass this one, and the state that you're going to generate distill all of these words in one vector. Okay, this vector is your context, okay? You pass this context to the decoder, and decoder is another RNN. So your decoder takes this constant, which is a representation of the whole sentence. It also takes an observation, and at the beginning of the sentence, this observation could be a fixed token, which tell the RNN that I'm going to start a sentence. So I'm going to start a sentence given that I have observed, all of these words before. So generate a word in the target language for me in French. So it generates this French word, which is I basically, and then this goes to next unit. This basically goes to, that would be my new observation, which goes to my unit, and the next word will be generated. Okay, and the same thing will happen. So the only information that I pass to my decoder, the only information that I pass to decoder is just this context vector, okay? And I assume that this context vector summarized the whole sentence that I had in the source language. Okay, this is sequence to sequence model. So this sequence to sequence model is basically, explained pretty well in this movie. I got it from Jay Alamar's blog, quite interesting blog. I suggest that you look at this blog to understand the concept of attention. So as you observed in this video, when basically words goes in, when a word goes in, the only thing that we generated was this vector, which will be passed to decode. Okay. Okay. Yeah, only this one will be passed to decode. Okay, there are problems with this approach. That was quite interesting approach at the time, but there are problems with that. And the first problem is the problem of long-range dependencies. What do we mean by the problem of long-range dependencies? Um, suppose that your sentence is not a short sentence, it's a pretty long sentence. And the only thing that we pass to decoder is the last hidden space of encoder. And we are hoping that this last hidden space of encoder captures all words in the sentence. But, you can intuitively appreciate the fact that most likely, if words are pretty far from this position, beginning of the sentence, somehow has been forgotten by the time that I get here. Sometimes my task is not just translation, is sort of more complicated task. I'm doing question answering, and I have a big text, and I'm asking a question, and the answer of this question is somehow at the beginning of this text. And the only thing that I have is this vector, which I generated at the end of this piece of text. And all information that I had here at the beginning somehow has been forgotten. So that's the problem of long-range dependencies. And gated models like LSTM and GRU somehow try to address this problem. But still, the problem exists, right? Another challenge is the sequential nature of this model. Words comes one by one and will be generated one by one. And so there's a sequence here, and it's not easy to basically parallelize the process. And so it makes the training slow, right? I have GPU, the GPU needs to do everything in parallel. I have TPU, TPU needs to do everything in parallel. But the nature of my model doesn't let me to do so. There are other problems involved with RNN, like the problem of vanishing gradient and exponential gradient and so on and so forth, that you're familiar with that. Exploding gradient, we address in the lecture of RNN. Okay, so what is the solution? One solution was proposed in 2014 in the area of natural language processing. This is not, this image is about computer vision, not natural language processing, but I just want to convey the concept. If, as a human being, not just a model, you want to say something about this image, you are attending to a part of this image, and you may think that if someone asks you what is this image about, you may say that it's a stop sign. Okay, so basically you're attending in this part of the image. There are many more details in this image that you're not talking about because you think this what's important in this image is this stop sign. Or if someone asks you what's this image, you may pay attention to this part, which is a boat, and forget about or don't pay attention to the rest of this image, like these details. Okay, so attention basically means paying attention or giving focus on, important factors of data. Okay, um, in a sense, I can say that attention is just a fancy name for weighted average. The concept of weighted average is quite important. You can see that, I can generate this image from this image by taking weighted average of all pixels, giving more weights to the pixel in this area and giving the less weight to pixels on any other part. Okay, so attention is basically weighted average. Have this in mind up to the end of this course, this lecture. So these are two important papers by the first one by uh, Badana and his co-authors in 2014, which introduced the idea of attention in natural language processing, particularly in translation. And that was another paper in 2015 that extended the concept. Okay, so let's look at a sequence-to-sequence model with attention in sort of basically, high level. In high level, in vanilla sequence to sequence model, I was feeding this word, but, eventually I had one vector passing to decoder. But here I don't have one vector, I have three vectors. And these three vectors are all hidden space of, my encoder passing to decoder. Okay. So somehow my decoder has information of all hidden space, not the last one. So intuitively, you can see that this can address the problem of long-term dependencies. So if I have a long sentence and the last one has forgotten the beginning, if my decoder somehow have access to all hidden spaces, then if I need information about, a part of the sentence in the past or a part of the sentence at the document in the beginning, since my decoder has access to all of this information, so it may, help the problem of long-term dependencies. In fact, we are not passing all of these three vectors to the decoder. We are passing a weighted average of these three to the decoder. And in each step of decoder, when I want to predict this word, or I want to predict this word, I compute a weighted average of all of the state of the hidden state and then pass it to a decoder. Okay. So attention, so we can think of attention as a function which takes some vectors and compute a weighted average of these vectors and produce a new vector. Okay, and there are other set of weights, and there is another set of weights. Okay, that's what attention does. This paper in 2014, and this is the title of the paper, it's the name of the paper, Neural Machine Translation by Jointly Learning to Align and Translate, uh, has this simple but elegant idea that I'm going to explain now. You know, when you want to do translation or you want to do prediction for a sequence, this is conceptually, what you need to do. You need to compute a conditional probability. Say, for example, you have a sequence of word, I am student, okay? And you're at this position. When you're at this position and you want to predict this word, and say this word is yi, you want to predict this word, you have to condition on all of the words that you have observed so far. Okay, you have to condition of all of the words that you have observed so far. So in practice, the way that we do this is to do it through uh, a function g. So we have a function g which compute this conditional probability. And in practice, in sequence-to-sequence model, this function g is my decoder. So it's RNN, or it's all LSTM, okay? So this function, this LSTM or RNN, is the function which compute this conditional probability. How does this function compute this conditional probability? At a step I, you know, when I want to predict the word student, which supposedly should be conditional probability on previous words, I don't really have these previous words, right? The only thing that I have, you know, because the only thing that I have is a hidden space, you know, because they go through RNN. I goes here, M goes here, you know, and each of them, you know, basically make a hidden space. The only thing that I have this is this hidden space, and I call this hidden space Li. Okay. Let's use this color. The only thing that I have here is Li, and Li is combination of the words that I have observed so far, okay, in my decoder. I have access to the previous word as well. I have access to this word because, you know, in the unit of LSTM, I have this word. I have this hidden space, which I call it L, and it's supposed to predict a new word, which is this word, student. Okay. What else do I have? I have C. So C is the context vector of my encoder. So I had an encoder here, which took in, say, a French sentence, produce a context vector. The context vector goes to this decoder. So my decoder has access to this context vector C, has at the position I had access to the previous word, yi minus 1, and has access to this state, right? Okay, that's vanilla sequence-to-sequence model. Okay, what about sequence-to-sequence with attention? The sequence-to-sequence attention, instead of C, has access to Ci, when Ci is a linear combination, you know, C was the last hidden space. But Ci is weighted sum of all states. Okay. So that's the difference between sequence to sequence with attention and vanilla sequence to sequence model. Okay, what's important here is in this weighted sum, how can I compute this weight such that these weights are meaningful, you know, such that the CI is a meaningful CI, is a meaningful weighted average. We are going to have, I mean, or what has been introduced in this paper is a similarity function which compute the similarity between all hidden space of encoder and the previous hidden space of decoder. So at the output position I look at all input positions of J, and I look at the similarity between hidden space of all of J's position in the input with I minus 1 position at the output. With the similarity, it could be a neural network, for example, which compute the similarity between these two. What is the weights of this neural network? I'm gonna learn it through, end-to-end process when I have like pair sentences in French and English, and I'm passing this through my encoder and decoder, and I learn the weights of encoder and decoder. I also learned the weights of this neural network, which computes the similarity between these two hidden space. I mean, this hidden space of encoder and decoder. Okay, so basically, this similarity tell me how important Hj is, how important Hj is if I want to predict L. Sorry, if I want to predict Yi, which depends on L. Okay. So suppose that I have this similarity function. So the next step would be to compute uh, softmax over this vector of similarity. You know, I had H1, H2, and H3, and at a certain position, I computed the similarity of Li minus 1 with these three. So I have a vector of three values, and these true values, I compute a softmax on it. And this softmax give me some sort of distribution, you know, tell me this weight is more important than these two. So it gives me basically, you know, some sort of probability. They're all positive and they sum to 1, right? Okay. Now, I'm going to use this A as coefficient for HJs. So basically, it tells me how important HJ was to predict Yi, which depends on Li minus 1. So if a particular Hj, so for example, if H2 was so important, the coefficient is large. And if H1 was less important, the coefficient is low. You know, if this neural network has been trained correctly, then that's what's gonna happen. So I have this weighted average, and this weighted average goes, compute this CI for me, right? So in word embedding, in word to vec, for example, which we haven't learned in this course, but you know the general concept was in the introduction. We observed that simple mathematical operation on word embedding has a meaning. You know, when I say that we pass I to the to R and N, pass M to R and N, so we have a representation of I as a vector. So we have word embedding. So we embed word to a vector space and pass them. So we haven't learned how to embed words yet, right? But you know the general concept, you know, word to vec uh, make this representation for you. And in word to vec, we observe that, you know, there is interesting relation between these words. Uh, you know, you can subtract man from king. The vector represent the man. You can subtract it from king and add woman to this, and it's going to be queen. So operation is meaningful here. So the same thing here, you know, this H is a representation of all of these words, and you can imagine that adding them up or even weighted sum of them has some sort of meaningful representation, produce some meaningful representation. So in a sequence to sequence with attention, I'm gonna pass the CI to the you know, encoder at the time. So it helps the problem of long-term dependencies. It was quite useful in practice in many tasks. I just explained this that when you are basically um, basically when you want to predict position I, when you want to predict position I in your output, you have to look at all positions J of your input. Okay, and you compute the similarity of the hidden space of decoder to predict I with all of the hidden space of your encoder. Okay. Uh, so I think explained this part. You know, you have this hidden space. It goes through similarity. It generates some values, and this values goes to a softmax, produce some probabilities, and then these probabilities would be weights of the hidden space of the encoder and produce, you know, a new vector, which is your CI, and this CI will be used in your function to estimate this probability. Okay. Uh, okay, you can see the effect in this picture, which comes from the same paper. You know, the task was translation, and we have a sentence in English, and we have a sentence in French, and you can see the alignment as, you know, the alignment of the words here. So when we compute this coefficient, it seems that a word in English attended the corresponding word in French. Okay, a word in English attended the corresponding word in French. But here, for these three words, you can see the order has been reversed. Why the order? You know, you don't see the same pattern. The pattern has changed here. Why the pattern has changed here? Because European economic area in English, when you want to translate it in French, you have to reverse the order of words. So it means that the attention mechanism worked correctly. So when it wanted to predict the word European, it gave high attention to this word, right? It didn't give high attention to zone, because if it was just uh, the same pattern, it should have uh, attended toward zone, but it didn't. It attended toward European. And the same thing, you know, economic here attended to this word in French. So it did the correct thing, you know, and it was, you know, increase the performance of these models greatly. Now we have to learn another concept, self-attention. You know, so far we had attention between source and target. We had attention between English sentences and French sentences, right? But it's a new concept, self-attention, attention between words of only source, or attention between words or only target language, attention between words of a sentence. Okay, we know the general concepts of word embedding. We know that we can represent the word I in a vector as a vector. We can represent word am in a vector, student as a vector, teacher as a vector. But that's not sufficient to understand a sentence. When you want to understand a sentence, sometimes you have to combine some of these vectors together. So you need some sort of composite embedding rather than just, individual embedding of the words. You need to combine words. This was introduced first in 2016 in this paper, Long Short Memory Network for Machine Reading. The concept of self-attention originally introduced in this paper. This is a part of abstract of this paper. Basically, the paper says that we want to, we propose a machine reading simulator which processes text incrementally from left to right and performs shallow reasoning with memory and attention. Okay, let's see what this mean. Basically, it means that when you read a sentence from left to right, to understand a word here, you need a composite, you need a combination of previous words, not just a single one. You need to understand how words relate to each other, okay? For example, if you have this phrase, a hungry man is an angry man, and suppose that you have word embedding for hungry and you have word embedding for man, but hungry man is a concept different from hungry and different from man. Combination of these two words together has, is a notion. Hungry man is a notion, is a concept. And if you want to understand why this man is angry, you need to know this combination of these two words, okay? So that's what this paper tries to do. In this image from this paper, actually, I think is quite, telling, actually, that's what they meant. In this picture, the red word is the word that you are reading at the moment. At the moment, I'm reading this word, D. In the next row, at the moment, I'm reading FBI, okay? So red is the word that is read at the moment, at the current time. And the blue word is just our memories. Forget about machine. You are reading this sentence. Blue is your memories about what you have read so far. And shades, basically different shades, represent the degree of memory activation. How much you put emphasis on this word. So say, for example, you're reading is. In the sentence, the FBI is chasing a criminal on the run. So you have read these two words, the FBI is. When you say is, your memory focus on FBI, right? When you are reading chasing, your memory focus on FBI is chasing. Who chased someone, you know? FBI is chasing. Who is chasing? FBI is chasing. Um, and you know, you can look at other rows and basically appreciate that this chase has some sort of meaning for you as a human being. So we want to mimic this in a machine, you know, the way that we uh, pay attention to different part of a sentence, the way that we attend to FBI and ease when we are reading chasing. We want the machine to do the same thing. We want the machine to attend to FBI, to attend to ease when we are reading the word chasing, okay? So that's basically what they have done in this paper. Um, they somehow defined a generalized way or generalized definition of the concept of attention. Okay, this three concept, you know, value, query, and key. It's not in that paper, and it's not in 2016 paper. It was introduced in 2017 paper, attention, all you need. But the concept of value, query, and key originally comes from, you know, the way that we search in a database. Okay, for the moment, forget about neural network, forget about deep network. Just imagine that you want to search in a database. And in database, you have some values and you have keys, index. Say, for example, you have keys of these values, not index, sorry, you have keys of these values, and you have a query. When you have a query, what are you going to do? You are going to compare your query with all of the keys in your database. And if a key matches, say this key matches your query, then you are going to report this value. Okay, you're going to report this value. So that was when the match between query and key is deterministic, like you have hard match. So there is one key which matches the query exactly. So if you have a similarity measure between keys and query, then between this query and this key, the similarity function return 1. And for similarity between this query and every other key, return 0, right? If you have such a similarity function, then if you multiply the similarity between Q and all of the KI's to value of YI, then it returns this particular value, right? Because the similarity between this particular key in this query is 1, and everything else is 0. So if you multiply this by VI, then all of these multiplication are going to be 0, and this one times value n is going to be value n. So if you take summation of this, then basically, you know, you have this value. You have the value n, which matches this particular query. You can assume that this process is not, you know, hard similarity, somehow soft similarity. And if it is soft similarity, it's not that the similarity between the key n and query is 1 and everything else is 0. So this is a large number, 0.8, but other keys have a little bit of similarity. This is 1.0.1, and this is other one is 0.1, and others are 0. Again, if you take this summation here, you have a weighted sum of values of keys that have some sort of similarity. So you have weighted sum of VI, and weights will be computed by this similarity function, right? Now, you may appreciate the similarity between these and the attention that we were explaining. We have a similarity function to compute, to basically compute the weighted average of our values, So we can define the concept of attention that we were talking so far in a general form. And in this generalized definition, attention needs three concepts: query, key, and value. And attention is going to be computed using this function. Okay. So you have a word in a sentence, say chasing. Okay. And chasing is now your query. Other words which comes before chasing, which was two words, or I don't know, three words, the FBI, the FBI is, these are all keys. Okay. So chasing is query, and all words come before that are your keys, and you have a similarity function which compute the similarity between these three words and your query, right? And use of them to find a weighted average of value. Okay, what's value? Value is also chasing, a representation of chasing. Now, it might be confusing that, chasing was query and chasing was value. So basically each word is query, is key, and is value. So as if we have three different representation for each word. Okay. Let's see if I can explain it here. We have word representation for each of these words. Let me call this X. Okay. I have word representation, which is vector. For D, I have a vector for FBI, and I have a vector for is. This is my word representation. So I'm going to compute a query for this representation, and this query is projection of this word to a new space. Say, for example, EX is in RD, is in D-dimensional vector, which represent each of these words based on my word embedding process, which could be, say it's word2vec, right? In practice, it's not word2vec anymore. Word2vec was the state of the art. But now we are using word embedding through basically end-to-end models. But whatever the way, it doesn't matter. Somehow we calculated a word embedding for each of these words. So we have D-dimensional vector representing each of these words. So X is in RD, and then Q, which is my query, is in RP is in p-dimensional space, but I'm going to compute the vector Q, okay, by a projection. So I have a projection matrix WQ, which multiply by X make Q, okay? So WQ transpose is a Q by D matrix, okay? I have K as another vector, which is also in RP, okay? And K is also computed by a projection, but this projection is different from the projection that I use for query. And also I have value, which is p-dimensional again, and this value is again, a projection. So you can think of this as a single word has three representations. Sometimes I look at this word as a query. Sometimes I look at this word as a key. And sometimes I look at this word as a value. And the word, a single word chasing, as a query has a different representation of the word chasing as a key, has a different representation of the word chasing as a value, okay? And self-attention means that look at chasing as query, compute the similarity of chasing as a query with all of these words. When you look at these words as key, okay, compute the similarity between this query and all of keys. And when you computed the similarity, compute the softmax and use this softmax to compute the weighted average of all of V's. And what is V's now? All of these words, but all of these words has a different representation as a value. Now, the new, basically, the value of chasing is a weighted sum of values of D, FBI, and is, right? So it might be a little bit confusing, and I don't have the chance to ask you, is there any question? Because when I'm teaching, I used to ask frequently, is there any question, to make sure that, it's a right pace, you're not lost. I don't have this opportunity. Actually, it's kind of weird experience, like performing for empty theater. It's a quite a weird experience. So I'm hopefully you're not confused by this, that a word can have three different representation, but I think it's going to be more clear later on. So we are computing the attention of each word to other words of the same sentence, and that's why it's called self-attention. Okay. Yes, as I explained, we compute the vector which represent chasing as a query, this which color should I use? Okay, let's use this color. Chasing. Oh, yes, chasing. I can't come back to the previous slide. Sorry. So chasing as a query with D as a key, with FBI as a key, and so on and so forth. Okay. When you compute this, when you compute the softmax of Q of word chasing with D, when you compute the similarity, and then you compute the similarity of chasing with FBI and with is, you get three basically similarity. You compute softmax and you get scores like similarity, which sums to 1, and all of them are positive. Then you are going to use them as coefficient of these three words, D, FBI, is, but value representation of these three words, and that's going to be value representation of chasing. Okay. So if I want to show everything that I said in this generalized definition of attention in a neural architecture, we have some keys, and we have a query, and then we are computing similarity between this keys and query as a similarity function, and this similarity function could be different things. So in some cases, the similarity function is a neural network, but in this new attention model, similarity function is basically dot product. So dot product between two vectors is a measure of similarity. In transformer that we are going to learn later, this dot product is the similarity function divided by square root of d, when d is the size of the vector. Okay. So in our notation should be actually p. So divide by square root of p. So it has, we may talk about this later. It's not that important. The important part is that this dot product is a measure of similarity. Somehow you normalize it, because if you have a long vector, you don't want, the dot product would be large, and if you have short vector, the dot product would be small. Somehow, basically, you want to normalize it. So you may have weighted dot product, and you may have many different type of similarity measure. Okay. So then when you have this, you go through a softmax, and softmax, use all of these similarities to compute the basically coefficient, and then you have this coefficient, then you use it as weighted sum for the values, and that's going to be basically your new value. Okay, that's just a neural structure of what we have. Okay, let me show you everything with matrix notation. I told you that so we have this x in d-dimensional space, right? And then I need a key, and key is another vector in p dimension, and I have a query, which is another vector in p dimension. I have value, which is another vector in p dimension. And as I said, k would be projection of x through a projection matrix. And this projection matrix, I'm going to learn the values of this projection matrix through my learning process. When we talk about transformer, it becomes more clear. So we compute Q through another function, another projection, and we compute V by another projection, right? And all of these W's, basically the dimensionality of them is D by P. So the transpose would be P by D. So the transpose would be this one, going to be P by D, and this is D by 1, and this is going to be P by 1, okay? Now, suppose that I put all of the x's in a matrix. So I have x1, x2, up to xn. So I put everything in a matrix. So this matrix is D by n. So if I have n boards, and I put all keys in a vector k1 to kn, and it's going to be p by n, right? And I'm going to have matrix Q, which is Q1 to Qn, and it's going to be P by n, and I'm going to have V, V1 to Vn, also this is going to be P by n. So the way that we compute attention is in fact to compute Q transpose K, which is dot product. So you can divide this by the length, and then compute softmax and multiply this by V. This is going to be your new value. Let's call it Z. Okay. So Q times Q transpose times K, K is P by N, right? K is P by N, and Q transpose is N by P. So this is going to be N by N matrix. And when you do softmax, it's as if you are normalizing this matrix such that the rows of this matrix sums to 1, and they're positives. So basically, you make this matrix a stochastic matrix. That's the definition of a stochastic matrix, the matrix which has positive values and sum to 1 row-wise. And then you multiply this by V, and V is P by N. So you have P by N times N by N. You're going to generate Z, which is P by N. Okay, and this Z is the new values. But this new values is summation, this is P by N, this V is P by N, and these are V1, V2, up to Vn. So basically, when I compute the Z1, the Z1 would be summation of V1 to Vn with this coefficient. So it's weighted sum of all of the words, all of the words when we are looking at the words as values, the value representation of the words. Okay, so basically that's what the generalized form of attention is. Okay, we so far we just talked about attention in natural language processing. The last part, let me mentioned using attention in computer vision. So attention has application in computer vision as well. So it was introduced, I mean, the concept of attention was introduced in mm, like computer vision for the first time in 2016 in this paper, Show, Attend, and Tell. So the idea is pretty similar to the idea that we had for in natural language processing, basically in the idea that was introduced in the first time in 2014. So the first version of attention that I explained to you, which makes a vanilla sequence to sequence to attention-based sequence to sequence, sequence to sequence with attention. So the model for image captioning is basically an encoder decoder. An encoder is a CNN uh, and a convolutional neural network, and the decoder is LSTM. Okay, so our domain information, in sequence to sequence, our domains was French, target was English. Now our domain is an image. The target is a sentence in English, for example. Okay. So again, the concept of common representation is that there exists a common representation, context, which can be represented, the same context can be represented as an image, or it can be represented as a sentence. Okay. And I need encoder to encode this sentence, this image, to a vector such that this vector can be translated back to a sentence, can be translated to a sentence, right? By a decoder. So the same concept that we had before, but instead of having two RNNs, I have one CNN and I have one RNN in image caption. Okay. So that's basically the model. And this model, for example, take this image as input and produce a caption of this form: a group of people shopping at an outdoor market. Okay, so explain what this image is, right? So how do we do this? As I said, the general concept is the concept of encoder decoder. So I'm supposed to turn this image to a vector such that this vector is a common representation between domain of images and domain of text, so it can be translated to text later on. So, but they used the concept of attention here. How did they use the concept of attention? So they had a CNN when they feed this image to CNN. So they are using the lower layers of CNN. CNN has many layers. They're using lower layers of CNN as some sort of feature representation. And this feature representation has some spatial information, means has information about different location of this picture. So what do we see in the feature space of lower level of RNN, represent this area of the image. Let's call it V1. And there is another feature which represents this area. So different parts of the image, information of different parts of the image appear in different vectors. If we look at the features that has been learned by lower layers of CNN, okay? So let's call these vectors annotation vectors, okay? So annotation vectors are some d-dimensional vectors representing spatial information, different parts of the image. Now, I want to translate this image to a sentence, and I have RNN which produce a sentence for me. exactly similar to the idea that we had in the first appearance of the idea of attention in natural language processing. Let's find the similarity between the hidden space of the target with these annotation vectors, because these annotation vectors are vectors which represent different parts of the image. So when I'm predicting a word, I want to see the hidden space of this LSTM is more similar to this part of the image or this part of the image or this part of the image, which part of the image is related to the word that I'm generating at the moment. So again, I have a similarity function, which I'm going to learn through the process of learning, which computes the similarity between this hidden space and annotating vector. And this is a neural network. When I computed this similarity, exactly the same as what we did before, we compute the softmax. We use this softmax to compute the new value. But in order to compute the new value in the natural language process, we just had a weighted sum of V, right? So we need a more complicated way. It's not just a simple weighted sum, it's a function Q, which we are going to learn, right? And this function Q is not just a simple weighted sum, is a function of these coefficients and these annotating vectors, so it might be nonlinear, who knows what the function is. We are going to learn this function. So pretty almost the same idea of what we had in natural language processing, and it's produced pretty interesting captions. Say these are results from this paper, like elephants walking across a dry grass field. When you feed this image as the input, or when you feed this image as an input, a group of young people playing a game of frisbee. So of course, these are the two successful examples. In the paper, they showed examples that are not successful. The model fails to generate the right caption. But quite interesting result in that paper. So that was about attention. Uh, so to give you some sort of roadmap, we are going to talk about in next lectures, we are going to talk about word embedding in more details. We talked about word embedding as a general concept that a word can be represented as a vector. So we will learn about word-to-vec. Word2Vec used to be a state of the art, is not state of the art anymore. So in fact, usually we don't use Word2Vec for word embedding. Usually in end-to-end model, we learn a word representation, a vector representation for words. But anyway, it's going to be still pretty useful to learn about Word2Vec to understand the concept of word embedding. So we are going to spend some time on it. And after that, we learn about transformer. And transformer is a model, as I explained, introduced in 2017 in a very interesting paper. Attention is all you need. So far we learned how we can use attention for RNN, how we can use attention for CNN. But attention, all you need, basically tell you that you don't need RNN, you don't need LSTM. The only thing that you need is attention model. And using only attention model, they built a new structure which is called transformer, and transformer can be replaced. RNN can be replaced by transformer in most cases, and with much faster way to train without the problems of vanishing gradient and exploding gradient that we had in the past, with a much better memory of the the past that can handle long-term dependencies, can be parallelized. It can be, you can use GRU and uh, TPU to handle to train that. So it's pretty interesting and a real game changer. So we are going to spend a lecture on transformer, and also there are interesting models built based on transformer like BERT and like GPT 2 and 3 that we are going to learn about. Okay.